Now, moving on from where we were with color and temperature and so on, now let's move into the size and density of stars. We know that the diameter of the sun is 865,000 miles. Its radius, switching to metric system, 696,000 kilometers, or 6.96 times 10 to the 10 centimeters. So its volume, this is the formula for the volume of a sphere, 4/3 power cubed, and it works out to this enormous number here for the sun's volume. Well, its mass, we know its mass too by methods which we'll get to in another talk. Its mass is this enormous number, so its average density, rho, is its mass divided by its volume, or 1.41 grams per cubic centimeter, so a little denser than water. But that's its average density. That's not its density throughout its entire volume. At its core, it's very, very dense. At its outer part of its atmosphere, it's would be considered on Earth quite a good vacuum. And Teres, the red supergiant we've mentioned a few times, its diameter is enormous. It's 400 times that of the sun. It would stretch out, if it were at the center of the solar system, its outer layers would be between Mars and Jupiter, and a little closer to Jupiter than to Mars, about 350 million miles, a truly enormous star. Its density, mean density overall, is less than that of the best vacuum that we can pull in any kind of lab. Sirius B, on the other hand, Sirius is the brightest star in the sky. You can see it in the head of the Canis Major, the big dog, the greater dog, in the winter and in the spring. That's Sirius A. Now, Sirius B, you can't see that with the unaided eye. It's very difficult to see with a telescope, although in its orbit around Sirius A right now and for the next few years, it's going to be at its maximum separation. And if you really want to see the white dwarf that circles Sirius, this is going to be, from now for the next maybe 5 years, going to be the best chance to do it for the rest of its orbit, which runs about another roughly 20 years. I don't remember the precise length of its orbit, but it's if you want to see it, now's the time to do it. It's difficult to do, and you may need to put a diffraction mask over your telescope and try to see it between diffraction spikes. Well, Sirius B, the white dwarf, is about the diameter of the planet Neptune, but it has the mass of the sun, and so its density is enormous, 19 tons per pint. And a neutron star, such as in the Crab Nebula, the central star, the supernova remnant at the middle center of the Crab pulsar, the Crab Nebula, is a neutron star. It's made up mostly of neutrons, and its diameter is less than the diameter of the city of Memphis. It's about 10 miles, but it is probably more massive than the sun. Therefore, its density is almost unimaginable, 4 billion tons per cubic inch. I remember when I went out to, I was a kid, 10 years old, and I went out to see a long trip out to the American and Canadian West, and we stopped at the Grand Canyon. And on the rim of the Grand Canyon, I was too young at the time, I was 10 years old now, so I wasn't old enough to ride the mule down to the bottom of the canyon. You had to be 12 to do that. So I was stuck on the rim of the canyon while the other boy in the family, who's sort of a distant cousin, rode the mule down. And so I'm wandering around, and what am I going to do? Well, on the rim of the canyon, there is a meteorite. It's a nickel iron chunk of meteorite, and it looked like a chunk of slag. Because I grew up in Birmingham, Alabama, and you know, I was very familiar. I knew what slag was, a byproduct, very light stuff like porous rock that comes off of smelting iron. And it had a sign by there saying what that thing weighed, and it was about the size of a watermelon, I guess. And it said it weighed, I can't remember, it was a whole lot, and I thought, no way it weighs that much. So I tried to pick it up, and I thought, well, yeah, it probably does. Sometimes, you know, the appearances can be deceptive. The neutron star is very small, but it's very, very dense. Cygnus X1, black hole, mass greater than the sun. It has a diameter of 0. Black holes are points in space with no dimensions really, which is hard to get your head around, but that's true. So its density, since its diameter is 0, and you divide the mass by the volume, you get infinite or infinity. Its density is infinite because its diameter is 0, so its volume is 0. Mass divided by 0 is infinite. And we will get into all of this next time in stellar evolution. Now, just to review, this is from Bill Bussler's talk last time, distance determination to the stars by parallax. Remember that parallax is the difference seen from two different vantage points, such as your thumb at the end of your arm. Look at it from your left eye, and then you look at your right eye. It appears to shift against the background. Well, that's the same thing that we're doing when we're looking at stars from opposite sides of the Earth's orbit. For example, look at a star in January and then again 6 months later in July from 186 million miles distant. That is the diameter of the Earth's orbit. So that's your baseline. It causes the star to move back and forth against the background of the more distant stars. This is also very difficult to see visually. It's nearly impossible to see visually, and was one of a pretty persuasive arguments against the heliocentric theory of the solar system. That is, the sun being at the center of the solar system instead of having everything revolve around the Earth. But it was measured in the 19th century, and we'll get to that in just a couple of minutes. By using trigonometry, since we know the angle and we know the baseline, we can calculate the distance to some of these stars that are close enough to actually observe a parallax. Within a few hundred light years of the solar system, here's the diagram. We have, this is one astronomical unit, the distance, the mean distance between the Earth and the sun. Here's the angle from star A, which is closer than star B, and you can see the angle is greater to the nearest star, smaller to the more distant star. Depends on the distance, the farther away it is, then the smaller the angle of the parallax. And here again, this is not to scale, but observing in January and July, here's the distance that we want to find out. We know this distance and we know this angle. So we can calculate that. We've got a baseline of 2 astronomical units, 186 million miles, and then we know that the parallax angle is less than, to the nearest star, is less than 1 second of arc. This is why it's so hard to observe and measure. But suppose that one were there, one exactly. We had a measurement of angle of exactly 1 arc second. There isn't one there, but suppose that it were. That would be 1 parallax second, or parsec. That's where that term comes from. And it still grates on me when I look at the first of the Star Wars movies, and Han Solo brags that he made the Kessel run in less than 12 parsecs. That's like saying I made the Kroger run in less than 2 miles. It's not a measure of time, it's a measure of distance. But we can calculate the distance to the star using trigonometry, using the tangent, because the tangent is, we know this distance here, the opposite, this is the angle, this is opposite. We know what this distance is, and we know what this angle is, so we can calculate what the distance is, what this this distance here is. This is the tangent, and you work all the trigonometry out. It works out to 1.92 times 10 to the 13th, or 19.2 trillion miles. Or if you want to express that in light years, that is light traveling 186,000 miles per second, and you divide that out, it comes out to 3.261 light years is 1 parsec. Now, as we mentioned, there aren't any stars exactly with one parallax, exactly 1 parsec away, or let alone any closer. And so the first man to do this was Thomas Henderson, who worked in South Africa, measured the parallax of Alpha Centauri, another star you can't see from Memphis, but you can from further south, in South Texas and South Florida and Hawaii and so on. You can see it, South America. In 1838, found it to be about 4 light years away, but he didn't publish until 1839, so he doesn't get credit for it as being the first one to see it. That's, if you publish first, or if you publish at all, you're the one that gets credit. For example, Galileo was widely given credit as being the first to see sunspots. He was not. There was an Englishman named Thomas Harriot who saw sunspots and documented them about 3 years earlier than Galileo, but he didn't publish. So Galileo gets the credit because he did. I mean, it doesn't do your science any good if you sit on your data. Friedrich Wilhelm Bessel was the first one to publish it. He measured the parallax of 61 Cygni, did a pretty good job of that. He calculated its distance to within just a small percentage of the currently accepted value, 11.4 light years, and he published first, so he gets the credit. And this is generally considered to be the beginning of modern astronomy, that is, modern, measured, carefully calculated astronomy. Then Struve measured the parallax of Vega, which is about 40 light, no, it's not that, 40 light years away. It's, what is the distance to Vega? I'm offhand, don't remember. But anyway, it's close enough that you can measure it without having a satellite in orbit. You can measure the parallax on photographic plates taken 6 months apart. They did it visually, without photography. But even that way, you can get useful results, not all that far from the solar system in terms of the galaxy, let alone the universe, only out to about 65 light years. If you let a computer measure the measurements on the glass plates in some observatories like the Harvard Observatory, Yerkes Observatory, and others have hundreds of thousands of glass plates on which they took photographs, and now we can go back and measure these carefully using computers and come up sometimes with new insights from old data. But with the Hubble Space Telescope and with the Hipparchus satellite, which was purpose-built to measure parallax of stars out to 500 or 600 light years away. And in Hipparchus, one of the things that it really wanted to measure with some accuracy is a distance to Cepheid variables, and we will talk very briefly about those tonight and then more in further installments. Now, as we see stars, their brightness depends on 2 factors. One is how bright the star is intrinsically, okay, its own brightness. And as we see it from here, it's distance from the solar system. So a point source obeys the inverse square law. That is, as you double your distance from it, its brightness decreases to 1/4 of what it was. Or if you're going the other way, if you half your distance to it, its brightness is 4 times greater. So the change in brightness is the inverse of that squared, and it is the inverse square law. And this makes it a little more easy to grasp by just visual. These are units, spheres. You can think of light being emitted from this point source as being emitted in spherical shells. And here's a radius of 1, 2, 3, and so on, and 1 unit. And you can see 2 units out, it covers 4 times the amount, and 3 units out, it covers 9 times, and so on. So it dilutes the light, spreads it out, like trying to zoom in on your cell phone and magnify a photograph. You get down to where you're just seeing pixels. Now, absolute magnitude is a way to sort of rank stars. We adopt, just by convention, a standard distance of 10 parsecs, 32.61 light years, and we pretend to observe each star from that distance. So we have to calculate it based on its distance. If its actual distance is 10 parsecs, then its absolute magnitude is exactly the same as its visual magnitude. It's absolute. The magnitude sub A is exactly the same, equal to the visual magnitude, m sub v. If it's farther away, it will get brighter if we bring it into that distance, and if it's closer, it will get dimmer if we move it out to that distance. Such as PARALLAX in Gemini. We know that its distance is 35 light years. We know that its visual magnitude is 1.16, and its absolute magnitude is exactly 1. Vega. Okay, here's the distance to Vega, 26.5 light years, relatively close. It's visually, it's almost exactly 0.04. Its absolute magnitude, because you're going to have to move it out to 32.6 light years, its absolute magnitude is 0.5. And again, in the case of PARALLAX, you're bringing it in just a little bit, so its magnitude would go up. And in the case of Vega, its magnitude would go down. Now, here's the equation. This is the absolute magnitude is equal to the visual magnitude plus 2.5119 times the log of 1 parsec in light years divided by the distance in light years. So the absolute magnitude for Antares, the bright red star in the heart of Scorpius, the Scorpion, we know its distance to be 520 light years approximately. We know its visual magnitude to be 0.92. So substituting in the formula here, you get these numbers, and it works out to its absolute magnitude. That is, if you could bring Antares to a distance of 10 parsecs, its magnitude would be negative 5.09, which is about 2.5 times or about twice as bright as Venus at its brightest in the skies of Earth. Now, here's something that, again, this is Delta Cepheid, the prototype or the sort of the namesake of the Cepheid variables. And this is one of the standard candles for measuring distances within the universe. And we're not going to get into that too much tonight, but knowing more about Delta Cepheid, we know that its visual magnitude on the average is 3.96. It is a variable star. And we know that its absolute magnitude is right at 4, which is pretty close to its visual magnitude, actually. So again, substituting in this formula and then solving for distance, we find that its distance is 1,275 light years. And that's important, and again, we'll get into all the reasons for that in another talk. Luminosity is it's like absolute magnitude in that it refers to the brightness of the star, no matter how far away it is. It is how bright really is this star intrinsically. It's the ratio of the amount of light that it emits to that emitted by the sun. Again, the sun here is the standard. The sun is 1. So it's a fraction or multiple of the sun's output. We know that the absolute magnitude of the sun, if the sun were moved out to 10 parsecs, its magnitude would be 4.84. That is, it would be so dim that you couldn't see it from Memphis unless we had a major power failure. That's about the same as the visual magnitude. The dimmest star in the Little Dipper's bowl, if you want to get a kind of a quick measure of limiting magnitude in the sky, look at the bowl of the Little Dipper, because the 4 stars in the bowl of the Little Dipper go in magnitude roughly 1, 2, 3, or 2, 3, 4, and 5. And this is the faintest one, almost 5. And we know that the luminosity of the star is a function of both its surface area and its surface temperature. And its energy output is given by this formula, the Stefan-Boltzmann equation. The energy in watts per meter squared is equal to sigma, this constant, times the 4th power of the temperature. The constant is this number in watts per meter squared in degrees Kelvin. Now we know the sun's energy output is this enormous number of watts. So if we can determine a luminosity of its star from its visual magnitude and its distance, and we know its temperature because we know its maximum wavelength, we've already covered that in the first part of our discussion tonight, we can calculate its surface area and therefore its diameter and its volume. So here's how you go about this. Star A and B luminosities are luminosity of A and luminosity of B. The magnitudes are absolute magnitude of A and absolute magnitude of B. And then this relationship is going to be true. That is, you divide the luminosity of A by B, it's going to equal the step between adjacent magnitudes, 2.5119, to the difference between the absolute magnitudes of the 2 stars. So if star B is the sun, again, the sun is the standard here, 4.84, we know that's its absolute magnitude. So the luminosity of star A is going to be this step between magnitudes raised to this power. So what about Sirius? We know the absolute magnitude of Sirius to be 1.45. Subtract that from 4.84. This is the sun's absolute magnitude, and raise 2.5119 to that power. It's 23. The luminosity of Sirius then is 23. Luminosity of Rigel, its absolute magnitude is a whole lot more. It's negative 7.1, very, very bright. So 4.84 minus negative 7.1, raise 2.5119 to that power. It's almost 60,000, much, much brighter. This is a very luminous star. And 61 Cygni, a much dimmer star, absolute magnitude of 7.5. Again, you do the calculation here, and it works out to almost 0.9. Now, in generally speaking, the more massive a star is, the more luminous it is. That does not always apply, and we'll talk about that shortly. And this brings us to one of the kind of the cornerstones of modern astronomy, the Hertzsprung-Russell diagram. Einar Hertzsprung in Denmark and Henry Norris Russell in the United States, around 1910, were both unknown to each other, trying to see if there was any kind of relationship between the absolute magnitude, luminosity of stars, and their spectral type, which is correlated with their temperature. They plotted these spectral types, again, O through M, O be a fine girl, kiss me, along the x-axis, the bottom axis, decreasing temperature, and on the vertical axis, they plotted the absolute magnitude, this is decreasing upward, negative numbers going upward, or luminosity increasing upwards. These are photographs of those two men. And they came to the same conclusion, that they found that most stars, instead of being randomly distributed in kind of a cloud, they were concentrated in a band from this hot, luminous part to the cool, dim part of their diagram. There were other concentrations of stars in other parts of the diagram. Some were cool but very bright, and some were dim but very hot. They were in opposite parts of the diagram. And then there were some scattered in a few other areas. And but even so, all that tells you something about those stars. This is the Hertzsprung-Russell diagram. And here you see the spectral class, and therefore the temperature. This is the temperature along here, but it's the same axis as the colors and the spectral designations. And then on the vertical axis, you have absolute magnitudes going from the faintest up to the brightest, and over here, luminosity as related to the suns, compared to the sun. So that here, 1 is by definition the sun, okay, the luminosity, and absolute magnitude, you'll see it's 4.84. But you'll see that although most stars are in this band, there are these stars up here. These are very bright stars, you can see, because their absolute magnitudes are up in here, yet they're also very cool stars, and kind of a paradox. Well, how could that be? Over here, on the other hand, you've got very hot stars. You know what their temperatures are because of their spectra, but they are also very dim. Again, well, what makes sense there? And what they thought was that all stars form up here, that all stars begin their lives as very hot, bright stars, and as they use up whatever fuel they burn, whatever they consume, and they didn't know what that was at the time. One idea was gravitational contraction, and one astronomer even said, well, if the sun were a lump of coal its size, then it would take this long to burn out. And well, geez, that doesn't make much sense because we know things are already older than that and so forth. They didn't know what was fueling the stars. They didn't know that it was nuclear fusion. That was an idea that just had not arisen yet. And they thought that all stars formed very hot and bright, and as they used up their fuel, they got cooler and dimmer, so that these would be very young stars, and these would be very old stars. And as it happens, they were mostly right about that, but for the wrong reason. So if they were thinking the sun is a nice middle-aged star, it's used up about half its fuel, and eventually it'll become a cool red star, and so forth. And that's where the early and late designations come from. For these spectral subclasses, they really are not early and late in terms of time, but more in terms of how close they are to the 0 point of each spectral category. Now, these stars up here were called red giants or supergiant. Red giants in here and supergiants up here, because the only way they could be that bright if they're that cool is that they must have a very, very large surface. That is, you only have so many lumens per square meter, and if you're putting out a lot of lumens, a lot more lumens for the same temperature, you got to have a lot more square meters. By the same token, down here, the white dwarfs were very hot, but they're dim, so they must be very small. That was the reasoning on that, and it was correct. Now, these are stars that are relatively near the Earth. The Sun here, Alpha Centauri, Sirius A and B. Sirius B would be down here as a white dwarf. Over here are the brightest stars. Some of them are fairly close to the Earth, but most are not. And this is where they appear on the Hertzsprung-Russell diagram. The Sun right here is the yellow G star. Its absolute magnitude 4.84. Over here, Rigel is a blue or blue-white star. Its absolute magnitude is almost -7. That's where it would appear on the Hertzsprung-Russell diagram. And they call this going back just a moment, another term you'll hear is the main sequence. That's that erroneous supposition that they had that this is the sequence of stellar development. That is, they all start hot and blue and they burn up whatever fuel they use and wind up cool and red, and that is the sequence through which they go. It isn't. They were wrong on that, but we retain that term main sequence, even though it no longer, it really doesn't describe what we want to describe. And how are all these stars related? Well, that's what Bill and Buster will cover in the next segment of the short course on stellar evolution. And with that, I will stop, and if you have any questions, I'll try to answer them.
Questions?
Yeah.